So we're now actually making the transition from all the theory that we've done about electric fields and forces and all of that, and bringing it down to the reality of wires and circuits and things like that. So this is the transition moment where we finally get from theoretically what a voltage is and what an electric field is to what happens inside of circuits, inside of real machines. So the first element that gets introduced is the capacitor, and the very word capacitance. Do I spell that right? Close enough.
Yeah.
Capacitance is, you can see the word capacity in there. Like if a jug has a 5-liter capacity, that's how much it can hold. In the case of capacitance, we're talking about holding charges. And a very nice way to hold charges is to have 2 plates or 2 pieces of metal, 2 conductors, maybe connected to wires. And if we put some positive charges on one of them and some negative charges on the other, can you see how the charges would want to stay there? There's no reason for them to run away, except for there is the slight reason that they're kind of next to all these other pluses, and that doesn't feel good if you're a plus. You want to get away from them. And this doesn't feel good if you're a minus. You want to get away, but you're also drawn to the ones just across the fence, right? So this configuration will hold those charges in place. Normally they would just disperse and run away. But because there's pluses next to minuses, they can be held there. You could say this is a positive charge, plus Q. You could call that a minus charge, a minus Q. These charges will always be equal. For every proton, there's an electron. Sometimes they just say the charge on the capacitor is Q, and it's understood that there's pluses on one side and minuses on another. Of course, the net charge in the whole thing is 0. There's just as many pluses as there are minuses. So capacitance is fundamentally a measure of how much charge could be held. It's not how much charge is held, it's how much could be held. Okay? So let's take a look at an important thing to visualize all of this. This is a site that actually I would highly recommend you start visiting like every chapter now that we're into circuits. This is the FET site from CU. So just type in FET, and they have visualizations of capacitors and resistors and batteries and things like that. So you can actually see what's happening to the charges inside of them. And we'll start by looking at this idea of capacitance. Remember, it's how much charge it could hold, not how much charge it does hold. And in a moment, this should be coming alive here. What is the problem? What is the problem? Problem solved. Okay, so right now you can see that this arrangement has a capacitance, it says, of 0.09 picofarads. And we'll talk about the units of that, the farads and some other things later on. I just wanted you to first get an intuition for what the capacitor does. We have some options here. Right now you could hold some charge, and actually let's turn the voltage on right here, and let's add a little charge to both of these. This looks like a sales job for Duracell to me, but it's just a battery. And I put a little voltage, and you see on the positive side there's some positive charges now, on the negative there's some negative. And do you think I could fit in a few more charges in there? Probably. There's space for them. I've got some sliders here, and notice though that when I added the voltage, did my capacitance change? No, it stayed the same. I can still hold. It does, because I added some voltage doesn't tell me how much charge I could hold. How much charge I could hold, it actually depends upon the geometry of these plates. If I make the plates bigger, can I hold more charge? And I will do exactly that. Let's slide this here. Can I do that? Bigger, bigger, big. And you can see clearly that you now can hold much more charge because there's more plate area. And look what happened to the capacitance. It went from 0.09 to 0.35. The capacitance just went up because the size got bigger. What happens if I What happens if I change the separation? If I get closer, can I hold more charge or less charge? What do you think? Look what happens when I go away. Maybe I'll make this a little smaller here. When I go away and when I go closer, can you see more charge getting on there?
Yes.
Look at that, densely packed charge. Why is that? Because there's more of the minuses to hold the pluses together, right? When we have these kind of separated, the force of attraction between the pluses and minuses is much weaker now, right? But when we get closer, those minuses will hold the pluses in place and vice versa quite a bit better. So the two key things for measuring how much capacitance, look, it went up again because we got it closer. What happens if I turn my voltage completely off? Does the capacitance change or remain the same?
Remains the same.
Remains the same because it was at 1.15 and it's still at 1.15 because it's just how much it could hold. So ultimately the capacitance, which we'll call C, is going to be depending on two things. It's going to depend on the area of our plates and their separation. Those are two fundamental things that can control how much you have. Which do you think, I'll put some various things, is it A times the area times the separation D? Is it A over D? Is it D over A? Which one of those makes sense? We want the biggest capacitance, we want a big area, but a small distance, right?
Yeah.
So which would it be? A over D. So we'll say that the capacitance is A over D. There's one little decoration that still has to go in there, and we'll get to that in a little bit. But fundamentally, that's going to tell you how much charge you could hold. Okay? Okay. Now let's look at now let's start adding some charge here. And notice that the more voltage I add, the more charge I get, right? And it turns out that that's proportional. It kind of makes sense. If we think about those parallel plates, and if we think about the voltage that's between them, that's going to depend on the electric field, right? The stronger the electric field, the stronger the voltage between those. And the more charge you have, the stronger the electric field, and therefore the stronger the voltage. You can see that as the voltage goes up on the battery, the number of charges goes up. And as the voltage goes down, the amount of charge goes down. It turns out that ratio it turns out that it's linear, I should say. The amount of charge that you see is going to be directly proportional to the voltage. More charge, more voltage. Less charge, less voltage. The constant of proportionality is C, which stands for the capacitance. So we have two alternate ways to think about C. It could be the ratio of the charge divided by the voltage, Q over V. And this is fundamental. But it's also related only to the area and the distance, and we'll finish that off in a little bit, but it's not going to happen today because we only have one more minute left. Now we can talk about the units of coulombs. Of capacitance. It's coulombs on the top and volts on the bottom, and we call that the farad. 1 farad equals 1 coulomb divided by 1 volt. It's an enormous unit. You will probably never in your life see a 1 farad capacitor. The capacitor that you guys just opened up, and this will be our last thing before we go, was they wanted to maximize the area, so rather than just having 2 plates in it, it was cylindrical, and what it was a plate and then another plate, but all coiled up inside of each other with a little paste to separate them so that the pluses didn't touch the minuses like here. So that's one technique of getting more capacitance, is to get more area. And one clever way to get more area is to make your big parallel plate capacitor and then roll it up like a burrito, like a turnover, like a marijuana cigarette, something like that. Okay, that is our good place to stop for today.
Wait, how much was it? The one that we had?
The